Section 3.2, working with derivatives. So we have a couple theorems here. They essentially say the same thing. If f is differentiable at a, then f is continuous at a. And if f is not continuous at a, then f is not differentiable. So we talked about, the meaning of a derivative. I posted a Khan Academy video of the conceptual meaning of a derivative. So now we're investigating the conditions where a derivative exists. So we have to have continuity. So places where a derivative or a function is not differentiable are places where it's not continuous, places where there's a corner or a cusp, and places where there's a vertical tangent line. Okay, so that has to deal with the fact that we define a derivative as a limit. So if the limit from the left and the limit from the right at a point don't match up, maybe there's a jump discontinuity, then that limit at that point does not exist, and so since the derivative is a limit, it also does not exist, and the function is not differentiable at that point. So let me give you a couple examples. Okay, so an idea of, something that's not continuous. Well, we've investigated that. We investigated that last week. So here's our point A. Suppose we have a jump discontinuity or something like that. So the function is not going to be differentiable at A because the limit from the left does not match the limit from the right. Okay? So again, a derivative is defined as a limit. Another thing to look out for is a corner or a cusp. So if we look at the absolute value function, okay, it looks like a V. So this is f of x equal to the absolute value of x. Well, hopefully you've seen that the absolute value of x can be written as a piecewise function, where it's equal to x for positive values of x, and negative x for negative values of x. And if you think about it, it's really two lines, kind of going tail to tail here. This is a straight line, x, and this is the straight line, negative x. The slope of this guy is 1. The slope of this guy is negative 1. Okay, I'm just thinking mx plus b. M here is 1. M here is negative 1. So at 0, where they meet, the limit from the left is negative 1, the limit from the right is positive 1. It's a jump discontinuity in the limit, and so the derivative does not exist at a corner. We would call that a corner. A cusp, let me draw an example of a cusp if you've never run into one. It might look something like this. Okay, so that would be a cusp at the point A, and it's really the same idea as a corner. Okay, the derivative, the limit from the left and the right don't agree. So that means that for a derivative, we essentially need smoothness in the curve and continuity in order for the limit and therefore the derivative to exist. Okay. The last scenario where we say a derivative doesn't exist is if we have a vertical tangent line. So if you remember from algebra, a vertical line has an undefined slope. So if it's an undefined slope and a derivative is a slope at a point, we can't really define the derivative when there's a vertical tangent line. So an example of a vertical tangent line would be the function root x. Okay, at 0, it turns out that this function has a vertical tangent line. And so it's differentiable everywhere except for 0. Okay, so those are kind of the scenarios where we're not going to have a derivative exist. Obviously, there's lots of different looking functions, but be on the lookout for these types of things. Okay, so one quick example. So here I've drawn out a graph of f of x, and I want you to graph f prime of x on the same set of axes. My recommendation is that you always do a little pre-work. So the first thing I'm going to do is I'm going to look at this graph and I'm going to identify where do I have zero slope. Okay, where is the tangent line? Where's the slope of the tangent line equal to 0? So hopefully you can see that the slope of the tangent line is equal to 0 at -3, -1, and 1. So that means that the value of the derivative function is 0 at those points. So we might as well go ahead and plot those. Okay. Next, I'm going to identify where we have an increasing slope or a positive slope and where we have a negative slope or a decreasing function. So we've got positive slope here and here. And we've got negative slope here and here. Okay, so how does that correspond to the derivative? Well, wherever the graph of the function is exhibiting a positive slope, our derivative graph is going to have positive y values. So that means it's going to be above the x-axis. Wherever our function has a negative slope or is decreasing, well, then the graph of the derivative is going to have negative y values or be below the x-axis. So let's analyze that a bit further. Okay, so from approximately -infinity to -3, we've got a positive slope. Notice how it's pretty steep here, okay? And then slowly it stays positive, but the slope value decreases. So what I mean by that is it's very steep here. Okay. And then as we move left, it becomes less steep and approaches 0. So we would represent that, I don't want to get it too messy here, okay? We would represent that as something that is very positive valued, that's slowly decreasing towards 0. So this, from -infinity to infinity, this red line represents f prime, and it shows that gradually the slope of our original f of x function, which is graphed in black, becomes less positive and approaches 0. Okay. Then the graph becomes negative. Notice that the steepest negative portion of the graph is in the middle here. And then, it starts really at 0 slope, it gets increasingly negative until we hit about -2. And then it starts to become, it flattens out and approaches 0 again. So we would denote that on our graph of the derivative by a negative valued region that goes from 0 to a negative value back to 0. Okay, similarly between -1 and 1, we start with a 0 slope, we go increasingly positive, and then we start to flatten out, become a little less positive until we approach 0 again. And then lastly, from 1 to infinity, we are going negative. Okay, so it starts at 0 and gets increasingly steeper in the negative direction. So we would denote that like this. Okay, so that's, one example of how to graph the derivative of a function just looking at the graph of the original function.